Ah, ah. Sì? Un minuto e poi partiamo. Intanto fate partire. Sì, 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 sì.
La sigla?
Ma falla partire.
Partiamo adesso?
Sì,
Allora,
sì, sì, sì. Bene, buonasera a tutti e benvenuti a questa prima serata con Trieste Next 2020. È una serata molto particolare con uno degli ospiti internazionali più importanti di questa edizione appunto del Festival della Ricerca Scientifica ed è importante dal nostro punto di vista come organizzatori per tutta una serie di motivi. Un anno fa l'ospite di questa sera, Peter Wadhams, era su questo palco per parlare, per presentare il suo libro che era arrivato tra l'altro secondo al premio Galileo per la divulgazione scientifica, un libro intitolato Addio ai ghiacci, che trovate tra l'altro una piccola promozione nel bookshop in Piazza Unità d'Italia. Ma al di là di questa piccola parentesi promozionale, un anno fa il tema, come tutti ricorderete, del cambiamento climatico era letteralmente dappertutto. Un anno fa Greta Thunberg, i Fridays for Future, erano un argomento all'ordine del giorno. Il cambiamento climatico, il riscaldamento globale erano nell'agenda politica internazionale. I grandi della Terra ne parlavano. Poi, come tutti sappiamo, a fine febbraio, primi di marzo, la nostra vita è cambiata e tra i tanti temi importanti anche questo tema è passato in secondo piano. Questo non significa però, così come gli altri grandi temi della ricerca scientifica, questo non significa che il tema del riscaldamento globale sia improvvisamente diventato meno importante e meno essenziale per la nostra vita, anzi le ricerche che stanno portando avanti a livello internazionale stanno anche dimostrando, come abbiamo letto in queste settimane, una certa correlazione tra la diffusione del coronavirus, del Covid-19 e i cambiamenti climatici. Vedremo nel futuro cosa scopriremo e cosa scopriranno gli scienziati. Però proprio per questo motivo noi abbiamo proposto a Peter Wadhams di tornare sul palco di Trieste Next per fare un passo in avanti sul tema, ponendogli una questione un po' troppo forse ampia, perché gli abbiamo chiesto: possiamo salvare il clima? Can we save climate? Forse una domanda ancora troppo aperta. Serata speciale questa, perché oltre appunto ad avere la presenza di Peter Wadhams qui con noi, mi diceva nel dietro le quinte che è il primo appuntamento dal vivo dopo il lockdown. Ha scelto proprio Trieste Next come primo incontro. L'altro elemento importante è perché proprio grazie alla collaborazione con Peter Wadhams e con sua moglie Maria Pia Casarini, che è vicepresidente di Polar Educators International, che è qui in sala, siamo riusciti a collegarci con un imprenditore che è collegato in questo momento da Los Gatos, California, Brent Constantz. I don't know if you're hearing us, Brent. Oh, here he is. Hello, Brent, and welcome to Trieste Next. Can you hear us? Okay, so we'll talk to you in a bit. And first of all, I wanted to give you the floor to Peter Wadhams, if you want to join me on stage. Finisco di introdurre brevemente i nostri ospiti di questa sera e poi lascio a loro la parola. Peter Wadhams ha un curriculum incredibile, uno dei massimi esperti dei poli, ha condotto 54 spedizioni polari di ricerca sul campo, 6 viaggi in sottomarino al Polo Nord, è medaglia polare di Sua Maestà la Regina Elisabetta II e ha ricevuto il premio W.S. Bruce della Royal Society di Edimburgo. È stato professore a Cambridge e adesso è visiting professor al Politecnico di Torino, dove è arrivato proprio da pochi giorni, mi dicevano, quindi motivo in più per ringraziarlo. There's one more reason to thank you for being here in Trieste, because we know that you just moved to Torino. So thank you for joining us here, and please join me here on stage, and a big round of applause for Peter Wadhams. Thank you, Peter. E alcune parole per presentarvi Brent Constantz, appunto collegato da Los Gatos, California. Brent Constantz è il fondatore e amministratore delegato di Blue Planet, poi capirete perché abbiamo deciso di invitarlo a dialogare con noi questa sera. È un Fulbright Scholar al Weizmann Institute of Science di Israele, è quello che viene definito dalla stampa un imprenditore seriale, uno dei pionieri della biomedicina, ha studiato e lavorato a lungo sul tema della mineralizzazione del carbonio in ambito ortopedico e poi negli ultimi anni ha deciso di focalizzare la propria attenzione su come questo processo, che è molto simile a quello che succede negli oceani con i coralli, con la barriera corallina, potesse essere utilizzato come strategia per combattere o per trovare una soluzione al riscaldamento globale e appunto alla presenza eccessiva di CO2 nell'atmosfera. Io mi taccio in questo momento, diamo la parola a Peter Wadhams. Brent Constantz, thanks for joining us here in Trieste Next tonight e buon ascolto a tutti. Thank you, Peter.
Thank you very much. And very happy to be here. This is, as the announcer has said, this is my first live conference after having had a long lockdown which I spent mostly in Fermo, which is a very nice town. Now, here we are. What I'm going to talk about is how we can save the world's climate. And in the talk I gave last year, here we are, which was based on my book, Farewell to Ice, which became known in Italy as Addio ai ghiacci. I was looking in that book at all the various ways in which the climate change is accelerating, generally related to our increasing carbon emissions, and what on earth can we do about it? And at the end of the book I said, well, the only way is to take carbon dioxide out of the atmosphere. Now, since then I've really looked more closely at this question of taking carbon dioxide out of the atmosphere, and at the moment I'm writing a book about this called, which will be called Mining the Sky, because basically it has to be a question of taking the carbon dioxide that's in the air, removing it from the air, doing something useful with it, and then we can bring the climate back to what it was before industrialization. And this is the only way that we're going to bring the climate back to a livable level, because if we do nothing but just emit carbon dioxide from our industrial processes, then the level in the atmosphere will keep rising, because carbon dioxide stays around forever, or thousands of years anyway, so that it doesn't disperse. If we stop emitting carbon dioxide, it doesn't mean that the climate gets better, it just means it stays the same. So we have to not just reduce the amount of carbon dioxide that we add to the atmosphere, we have to actually take it out of the atmosphere. And that's the challenge to mankind, is to remove, how do we remove enough carbon dioxide to bring the level down so that our climate becomes cooler and more sustainable, the way it was before we invented industry. So that's the theme really of today's talk, and we're very fortunate to have Brent Constantz with us, who is the entrepreneur and founder of one of the companies in the United States which is doing the very best work on carbon dioxide removal, because they've developed a technique which actually uses the carbon dioxide that's removed in a very productive way. So he'll tell you about that later in the talk. So let's talk initially, I'll run over again the problems that we're having with excessive emissions of carbon dioxide in every department of the planet, and the disasters that are happening, which is why we need to take the CO2 out of the atmosphere. If you want to see a nice movie about this, there's a very good one that was produced by Leonardo DiCaprio and called Ice on Fire. And he deals not only with carbon dioxide emissions, but also with carbon dioxide removal, which most official bodies don't talk about. But this is a film worth seeing, because he covers many different aspects of this problem. Now, the story starts with this very well-known set of graphs, which comes from cores drilled in ice in Greenland and in Antarctica, and it shows us just the history of carbon dioxide in the atmosphere. And it's a very strange one, because this was the carbon dioxide level over the last 400,000 years, and you can see that it went through cycles. Each of the cycles corresponds to an ice age. So we went in our climate from being very cold, that's an ice age with glaciers everywhere, and then the ice melted. We had an interglacial, which is a warm period, which we're in at the moment, and then you go to another ice age. And the strange thing that's come out of the data is that during the depths of an ice age, the carbon dioxide content in the atmosphere is lower, but it's always about the same value, about 180 parts per million. But then in the warm period between the ice ages, it goes up to about 280 parts per million, but it's also a very constant value. So the Earth seems to have two preferred modes of carbon dioxide, which depend on, of course, the growth of plants. One is the 280 level, which is in between ice ages. The other is the 180. So our 280 level carried on very nicely until we discovered fossil fuels and started mining coal and then oil, and started burning the fossil fuels, and that produced carbon dioxide. So the carbon dioxide levels were until about the year 1800, they were the same as they'd been 15,000 years ago, the same as they were when we came out of the Ice Age. The Earth was very stable, but then we started burning fossil fuels, and the level shot up to a state it had never been in since we started doing measurements, or since measurements were first taken anywhere. So it's up from 280, it's now up to 414. So that produces a drastic effect on the planet. These are the temperatures that go along with that. That's the Ice Age temperatures and the warm temperatures. And sea levels seem to follow that as well. When there's a warm period, sea levels are higher. And of course, at the moment, sea levels are rising very fast. So that's what we've been doing. And if we hadn't invented coal burning, we would actually be moving slowly towards a new ice age. These measurements were the average temperature of the planet over the last 1,000 years, and we can see that it was very slowly going down. We were actually heading towards the next ice age, although we won't reach that ice age for about another 20,000 years, but we were moving slowly towards it. Then suddenly, again, when we started mining coal, the temperature shot up, and nobody knew why at first. Not only did the temperature shoot up, but of course the carbon dioxide level in the atmosphere shot up, and the levels of other gases that affect the climate, methane and nitrous oxide, also shot up. Because we didn't know very much chemistry in the 19th century, nobody worried about this, nobody knew why it was, until 1896, when Svante Arrhenius, who was a Swedish scientist, from the newly discovered laws of the behavior of gases, he deduced that the carbon dioxide that goes into the atmosphere from burning fossil fuels actually warms the climate, and calculated how much warming there would be, and got answers quite close to modern answers. But he didn't worry about it either, because he thought all the extra carbon dioxide would dissolve in the ocean and would be harmless. So although he actually gave us what we needed to know to be worried about climate change, he himself was not worried about it. So we worry about it, but it's taken us a long time to take this seriously. And really, taking it seriously started in 1958, when the first continuous measurements of carbon dioxide in the atmosphere started from the top of a volcano in Hawaii, Mauna Loa, and they're still carrying on today. In fact, the son of the original Keeling, who did this, is still at work doing this. So we can see that the carbon dioxide levels have kept rising. It wasn't just one big impact from burning coal. It's been coal, oil, everything else, every other fossil fuel. We've been increasing our usage of them and increasing the carbon dioxide level faster than anybody has anticipated, and also faster than any international agreement. The most recent agreement was the Paris Climate Agreement here in 2015, and there were earlier agreements about limiting carbon dioxide emissions. None of them had the slightest effect. The CO2 level in the atmosphere, which is really a measure of how much warming the planet is suffering, has continued to accelerate upwards. It's been going up a bit like the COVID virus. It just accelerates upwards. And so nothing we've done up to now has really been effective in saving us. And we can see why, partly because these are the emission levels of carbon dioxide from different countries. And we can see that although the USA and Europe have reduced their emissions somewhat, China and India have just gone up really wildly, and they're the biggest contributors now to to increasing CO2. And so looking at what does that do to the planet, well, the first thing is if you warm the planet, one of the things you're going to do is turn ice into water. So we really need to look firstly at where there's ice and where that ice is disappearing. So one place is the Arctic and the Arctic Ocean. So here's the way the Arctic Ocean was when I was young. In the middle of the whole of the Arctic Ocean used to be covered with sea ice in the winter, and even in the summer, most of the Arctic Ocean still had sea ice. So it was a material which covered the whole northern end of the planet. But it started to, as the CO2 level rose, the sea ice retreated, and this is what it got to by 2012 in the summer, which is a long way further back from the way it used to be in the summer, which is the black line here. So we've already lost this huge area from the Arctic Ocean. And then this is the level last week, is mid-September of 2020. So it's further back even than the reduced levels we were getting at the beginning of the century. So it's continuing to retreat, and before long, there won't be any ice there anymore. This is this year's ice area. This is from the middle of winter to the middle of summer. The area of the ice goes down, and the dotted line was the average for the last several years, from 1981 on. But the orange line was the record year so far, which was 2012, and the red line is this year. Well, I should have written 2020 there, but you can see that for much of the year there was a record low area of sea ice, and it just came a little bit above that in September. So we can see that the decline of sea ice area is continuing. And the result, you already can see it if you go to the Arctic. This is what you used to find, huge kind of mountains of ice. This was called multi-year ice that's many years old. And it's very rugged, difficult to walk over, and it blocks the passage of the Arctic to shipping. But today, near the coast, it's very thin, and here, for instance, Inuit hunters using dog sledges are suffering real hardship because the ice is so thin that their sledges go through the ice, which can be a disaster for them. And we see, and we see also that even in the winter, the ice breaks up into with openings in the ice called leads all over the Arctic. So it's unsafe to try to walk across the Arctic or land an aircraft on it. We've been measuring the thickness of the ice and how that's been going down. The area is, satellites tell us the area, but to measure thickness you have to go underneath the ice and use an echo sounder, a sonar that looks upwards at the bottom of the ice. So we've been able to do that over many years, thanks to the cooperation of the Royal Navy that's allowed scientists to go on submarines. And I've usually been the scientist. So concluding from the thickness and the area, the volume of the ice has gone down by a huge factor. This is the summer volume of ice. 30 years ago, it was up here. Now it's down here. It's only a quarter of the volume of ice in summer that there used to be only 30 years ago. So that's the ice which we see before our eyes disappearing. But there's another kind of ice which is disappearing that's even more of a worry for people who live by the coast, which is the land ice, that's the glaciers and ice sheets on Greenland and the Antarctic, these are melting very fast, and that is ice which is on land but now goes into the sea when it melts, and that adds to the sea level rise. So the threat there is the rise of sea level, and here we see with the warming of the Arctic Ocean, that's the red, we have warmer air moving over the continent of Greenland, which is here, and the amount of warming that's going on in the Arctic is much higher than in low latitudes. There's a magnification effect. And one of the effects of that is that the Greenland ice sheet, which has an elevation of about 3,000 meters above sea level, therefore it's extremely cold on top of the Greenland ice sheet. Normally, you would never get any melting, even in summer. But now, you're getting melting over the entire surface of the Greenland ice sheet. The blue is melting, and typically in the past few years you would have melting around the edges, but now you get melting over the whole ice sheet. And you can measure how much ice is being lost by a new satellite method, which is called GRACE. It's a gravity satellite, and as the ice disappears from the Greenland ice sheet, it affects gravity, and you can measure that. So we know how much ice is disappearing, and it's accelerating. There's an accelerating loss. So I was lucky enough to be on the Greenland ice sheet last August the 1st, which was the day on which there was a record amount of melt in a single day since records began. So here's the ice sheet. You can see that it's already looking kind of rotted, and then it lost that day. It lost 12.5 billion tons of ice that melted off the ice sheet, all turned into water, which ran off in streams and waterfalls, and running through holes in the ice, ended up in the ocean. So that's another 12.5 billion tons of water in the ocean in a single day. And the reason why that happened was the air temperature was so warm. It was 21 degrees, which you could wear a T-shirt even though you're on the top of an ice sheet. And one of the reasons why it's speeding up is that as the ice melts, it leaves behind a huge amount of dirt. And this is dirt that's accumulated over hundreds of years of dust storms and dirt blown over the ice. It's dark. The water goes away, the ice melts, the water goes away, but the dirt stays, and the dirt gets darker and darker. So this is called black ice, and it's very extraordinary stuff. It's not slippery because there's no, it's more dirt than ice. But the dark dirt absorbs solar radiation very effectively, and that accelerates the melt. So this kind of ice is melting faster than clean ice, the clean ice that you used to get from snow falling on the top of the ice sheet. So now we see here's a layer of dirt over the whole of this ice sheet here. So what used to be the case that the main contribution to global sea level rise was the fact that the ocean is warming up, and that causes seawater to expand. But now what's taken over from that is the Greenland ice sheet and the Antarctic ice sheet melting and putting the meltwater into the ocean, and that's producing more accelerated effects on sea level than anything else. And so the predictions of how much sea level rise we'll get by the end of the century keep going up. This is the sea level rise since 1800. Doesn't look too bad. It's only 20 centimeters. But then the predictions of models got more and more. This was the Intergovernmental Panel on Climate Change, which produces complacent predictions, but then more and more measurements being made led to higher and higher values. And already we're estimating more than 1 metre of sea level rise by the end of the century. And in fact, most scientists think it will be much more than that, maybe 2, 3 or 4 metres. And that's going to really cause loss of a lot of cities, loss of coastal cities, well-known ones like New Orleans, Miami, and in Europe, Venice, despite the Venice gates. So that's nasty. And on top of that, there's a nasty effect on poor countries that can't afford to raise the heights of their flood defences. So this just shows what happens if you think of a spot in the ocean. The sea level changes with time because of wind and tides. So it follows this kind of curve. And right at the end here is the amount of extra height that would cause a disastrous flood. So that's the probability of a disastrous flood. But if you alter the mean, if you add more water so that the whole curve is moved to the right, then the probability of a disastrous flood goes right up to this value. And that's okay if you can build flood defences up by this amount. But if you can't afford to raise flood defences at all, or you haven't got any flood defences, like Bangladesh and other poor countries, you're going to get more and more floods, more and more disastrous floods, and this is already happening. Other effects that are happening, the warming of the Arctic is giving rise to melting of snow. So the orange here is areas that used to be snow-covered. You traditionally think of them as snow-covered, like Alaska and Siberia. You think of those places as cold, but now the snow goes, and again, you get more absorption of radiation. And of course, other effects that are included in that include these wildfires that are happening because of the warmer air temperatures. So in fact, I got caught in a wildfire, and it is quite frightening, mainly because you don't expect it, because this was California, and we were driving along the freeway in Pasadena, which is a city, and suddenly we saw this plume of smoke, which we thought was a building on fire, and actually it was a wildfire from a brush-covered area coming down into the town. So even a big city like Pasadena is subject to wildfires, and they close off the roads and cause general mayhem. Another effect that really worries people and worries me is that we might have a sudden big burst of warming due to methane being released from the seabed in the Arctic. This is because the Arctic Ocean is very shallow around its edges. This is only 50 to 100 meters. And that means that when the sea ice retreats in the summer, you have this shallow water that can warm up a lot because of the radiation from the sun. And we've measured here that you're measuring about 5 degrees. And this is a measurement that was done last week. The temperature we found here, which is right in the middle of the Arctic Ocean, close to this edge, this shallow water region, was 8.3 degrees. So that's very high, because when there's ice around, the temperature of the water stays at 0, even in summer. But when the ice goes, the radiation can warm the water up, and now you have 8.3 degrees water, which is almost warm enough to swim in. But that warm water melts the seabed. It melts the permafrost on the seabed and allows deep sediments, seabed sediments, to come to the surface. They turn themselves into methane gas, and the methane gas rises up in these plumes. This is a sonar picture of this. This is the seabed at 70 meters, and then this is the sediments underneath the seabed turning themselves into methane, the methane coming up in big plumes up to the surface, being released into the atmosphere. And methane is a very powerful greenhouse gas. So this really increases global warming. Here's some of the methane gas coming up against the ice. Now, a further effect, which again we notice in our lower latitudes, is extreme weather effects, which normally you think of weather as something that varies at random, while climate is the real change. But in fact, these weather changes are really climatic. What's happening is that there's a wind that separates polar air at high latitudes from warmer tropical air, and this used to be a very sharp boundary with a very strong wind, and that was the wind that you'd use if you were flying from the US to Europe. But now that wind has gone down because the polar air is so much warmer that there's not much difference between the polar air and the tropical air. So this wind slows down, and it allows polar air to come down into lower latitudes, like here, and it allows tropical air to go up to higher latitudes, like here in the Midwest. So you can get really unusual weather, unusually cold weather where it's supposed to be hot, and unusually hot weather where it's supposed to be cold. And we've known this in Europe, and in fact this is now a known effect all over the world. The trouble is that that's happening in the middle latitudes, and in the middle latitudes is where the world grows most of its crops. So the brown here is the density of crop production, and we see that the biggest density is in the Midwest of the US, in Europe, Ukraine, and Asia. And in all of these areas, the food production's been disrupted by these events of the jet stream. And the result has been a rise in the cost of food. The United Nations produced a food price index in the year 2000 that was set at 100. That's the average price of food everywhere in the world. So it was 100 in the year 2000. It reached over 200 by the year 2008, which is extremely nasty for people who have to spend most of their budget on food. That's people in third world cities. So this corresponded with a lot of unrest and revolutions in the third world cities. Also, that warming produces a decrease in the yield of all the major crops, which is also going to be very bad for feeding people. So what can we do about this? All of these things are due to increases in carbon dioxide levels in the atmosphere, and the only standard solutions that we've got and that have been proposed has been, let's reduce our emissions and get them done. And this is officially what we're trying to do, using renewable energy, using solar and wind energy, reducing our emissions. But even if we reduce them, we're not doing anything about cooling the climate. It's still warming. So the only way that I can see is that we have to take some carbon dioxide out of the atmosphere. So this is where, in fact, unfortunately, Greta Thunberg was brilliant at inspiring people to get something done. But so far, she's only talked about reducing emissions. But I think she'll be talking more about carbon dioxide reduction. So the first ideas were, why can't we reflect more radiation back into space? And one of the ways of doing that is this device that was developed by a Scottish engineer, which is where you pump water up this pipe into, and you have a nozzle to divide it up into fine particles and pump the fine particles into the bases of marine clouds. And that makes the marine clouds brighter. And when marine cloud is brighter, it reflects more radiation. So if you have a lot of these ships, which are unmanned ships, going around in the ocean, putting this water vapor into clouds, we could offset global warming. But we wouldn't be doing anything about the carbon dioxide. So what it boiled down to is, can we actually get rid of carbon dioxide? And the various methods have been proposed, which of course I'm going to end up with saying direct air capture is the best. But some of them look superficially attractive. And the first one is, why not just plant lots and lots of trees, afforestation? Because a tree is a machine to produce oxygen and absorb carbon dioxide. So a tree does just what you want. The trouble is, the amount of trees you'd need is out of range. This is a calculation of the areas you'd need to remove 8 gigatons, that's 8 billion tons of carbon dioxide per year, which is the amount of carbon dioxide emitted by Europe. So if you want to get rid of Europe's burden of poison, then you'd have to cover 6.4 million square kilometres of Europe with forest. And that's the whole of Europe. So Europe would have to become one giant forest if we wanted to get rid of CO2 by afforestation. So we can't do that. There are other methods in which we actually grow sort of biological waste products and mix it and use the waste products to capture carbon. It's called BECCS. And again, you use huge amounts of land to do it. A lower amount of land is needed by a technique which is crushing olivine rocks. Olivine rocks happen to be rocks that absorb carbon dioxide. So the idea is you crush them into a sort of sand and spread this sand everywhere. But the two problems are you'd have to spread the sand really everywhere. The whole world will be covered with sand. And the other thing is that when the sand has absorbed its carbon dioxide, then it's no use anymore. You have to throw it away and get some more sand. So that's not feasible. So what it boils down to is running air through a system that takes out the carbon dioxide, and then you have to do something with the carbon dioxide because we in our stupidity are putting over 40 billion tons of carbon dioxide into the atmosphere every year. So if we want to bring our climate back to a better level, we have to start by taking away 42 billion tons of CO2 and then take away more than that so that we get the level down. So we're taking over 40 billion tons of CO2 out of the atmosphere per year if we're using this air capture system. So if we do air capture, we have to do it on a vast scale. But it doesn't take a lot of space. You simply have the system set up in various plants that do this. So this is really the ultimate solution. The CO2 levels are high already, too high, and emission reductions aren't going to bring us any kind of relief. So we have to work out a way of taking carbon dioxide out of the atmosphere, and we have to be able to do it cheaply enough for it to be applied to the entire planet. So the ideal is to take away the carbon dioxide, but to turn it, not just throw it away or pump it underground, which can be done, but you turn it into something useful. And a very clever company called Blue Planet has developed a way to do this and turn it into artificial limestone, which is a rock that's can be used and ground up for cement production and a lot of other uses where we need huge amounts of this rock, and it's difficult to get it. So this is their idea, that we take the CO2 out of the atmosphere, but we turn it into something useful. So a leader in this program has been Brent Constantz in a company called Blue Planet in Los Gatos, California, and we're very pleased that he's agreed to not come physically from California, but speak from California and tell us how his company works and how they take carbon dioxide out of the atmosphere. Okay.
Thank you very much, Peter. That was a wonderful talk, and it's really a pleasure to join you today from California. The work we do at Blue Planet is, as Peter suggested, is really directed toward massive removal of carbon dioxide on the gigaton scale, meaning billions of tons of CO2. Our process involves both capturing carbon dioxide from a variety of different sources, as well as transforming or mineralizing the carbon dioxide into limestone. Yeah, we also consume a lot of waste resources like the demolition from buildings, for example. And we utilize that to transform the carbon emissions into the principal constituent of the most used building material in the world, which is concrete. I'd like to start off always talking about where all the carbon is in the first place. This is carbon, not CO2 I'm talking about, but the CO2 is reflective of that. In Earth's atmosphere, there are about 750 gigatons, 750 billion tons of carbon in the entire atmosphere. And if we look at the whole biosphere, all the land, trees, all the terrestrial biosphere, and all the marine biosphere, all the oceans together, you know, there's on the order of less than a 1,000 gigatons. If we go to the surface layers of the ocean, the mixed layer, also about 1,000 gigatons. In the soils, there's over 1,000 gigatons. And even when we get into the deep oceans, there's almost 40,000 gigatons of carbon. But when we get to the lithosphere of the Earth, the rocks in the crust of the Earth, there are about 50 million gigatons of carbon. And most of this is not coal, it's actually limestone. So if we look at where all the carbon is and where it's going, the atmosphere is always in equilibrium with the ocean. And if we lower the CO2 levels in the atmosphere, then there'll be net diffusion from the ocean into the atmosphere. And if we increase CO2 in the atmosphere as we're doing now, there's a net equilibrium to transport CO2 into the oceans. But the thing to remember is almost all the carbon is already in limestone for Earth. And if we look at limestone, it's a very well-tested building material, especially in a beautiful country like Italy. There are so many limestone structures that it's really quite impressive. So if we look at where most of the carbon is today, it is in limestone. Here's an example from the White Cliffs of Dover, which represents a few gigatons of carbon that was captured by marine organisms approximately 100 million years ago in the form of calcium carbonate, which now forms the deposit of limestone. When we look at what we're adding to the atmosphere today, we all know very well that we're adding about 40 gigatons of CO2 to the atmosphere every year, coming from a variety of anthropogenic sources. If we look at what we could do by capturing the limestone, the CO2, and turning it into limestone in terms of the impact on climate change mitigation and the cost to do it. In the upper right corner here, you see aggregate. And aggregate is the sand and gravel that is used in concrete, for example, the most used building material. And there's actually over 50 gigatons of rock mined globally, 50 billion tons of rock mined compared to the 40 billion tons of CO2 that man puts into the atmosphere every year. So aggregate, or sand and gravel, rock, which is mined, is actually one of the only reservoirs where we can actually put that much carbon dioxide if we want to sequester it. And what's different about rock is not only is it the most transported commodity, the largest commodity on Earth other than water, it's already used. It's been paid for already, and is possible to use as a reservoir for carbon dioxide in rich countries or poor countries, high latitude, low latitude, coastal, inland countries. Anywhere where man in any urban area is using concrete, there's a demand for rock, which is already being paid for, whether there's a carbon subsidy or not. So when we look at the built environment and we look at concrete, and we look at the incorporation of carbon dioxide into concrete, because it is the most used building material, there are a number of different approaches that have been evaluated because of the realization that concrete probably is the reservoir most suited to store CO2 that we've captured. Going on the left from just purifying CO2 and injecting it, which has very little impact, to on the right where we're taking the principal constituent of concrete, which is the sand and gravel, and replacing it with limestone that's been created by capturing CO2. When we look at all the different products that we can make out of carbon dioxide, there's one aspect is how close is the technology to employ, because whatever we do today, we have to do it quickly. It has to be implemented in the next decade. And aggregate has turned out to be one of the most feasible methods for capturing gigaton quantities of CO2. This is a chart which is meant to represent on the left the actual revenue potential of transforming carbon dioxide into concrete and fuels and aggregate and other things. But on the right is the actual impact on CO2. And far and away, putting CO2 into concrete as aggregates is really one of the most impactful methods we can use. What we do at Blue Planet is we have a pretty simple process. It differs from any other carbon capture process in that we don't capture CO2 out of and try and purify it. We simply convert it into carbonate, just like the natural process when the atmosphere equilibrates with the ocean. And that saves a lot of energy. It saves a lot of capital equipment and space and energetic use. So We have three main steps to the process. They're in a pumpkin color, the gas absorption, where we contact different gases. Could be raw flue gas from an industrial plant. It could be direct air capture. Our process is indifferent to where the CO2 derives from. We capture about 90% of the CO2 out of the gas, and we convert it into a carbonate solution similar to the ocean. And that's seen where it says carbonate mineralization. And then we utilize waste materials like used concrete to rejuvenate it and get calcium and make more product again. So it's a revolutionary self-contained system that we're using. Another aspect of what we're doing is we're taking the entire demolition of the built environment, which is mostly concrete, and instead of wasting it or landfilling it or using it for road base or a low value application, we're dissolving away and repurposing all the calcium. And in the coming century, this is going to be more and more important. A substantial amount of mankind's built environment will be affected by sea level change and will have to be demolished. And there'll be an enormous amount of not only need to rebuild further inland at higher sea levels, but a need for the raw materials to build those new cities. But our main product is our carbon sequestered material. And it's very similar to the formation of modern white sands that you see in the tropics, which is limestone. And one thing to note is limestone is calcium carbonate. And if you remember from your high school chemistry, calcium carbonate has a molecular weight of 100 grams per mole. And there's one CO2 in every calcium carbonate. So CO2 has a molecular weight of 44 grams per mole. So if I have a ton of limestone that I've made, I've sequestered 440 kilograms of CO2 within 1 ton of limestone. So these are the two materials that come out of the plant. On the left is limestone that's made from CO2 that would have entered the atmosphere, but is now permanently sequestered in the crystalline state in the limestone. And that's an important point. This is a form of permanent sequestration, just like the 50 billion tons of CO2 that are carbon that are in limestone in the lithosphere of the Earth. This carbon will not be re-emitted, as it would say if it were transformed into a biofuel and combusted. But also there's the upcycling of the raw materials on the right, and this shows upcycled rock. So instead of bringing more rock in for further aggregate from long distances and mining new quarries, this is a major aspect of the circular economy and reusing the building materials we're demolishing today and incorporating it in the mass flow. We started pouring this concrete at San Francisco International Airport about 4 years ago. This is for a significant airport near Los Gatos, where we're attempting to get to hopefully a carbon neutral overall structure by including carbon negative concrete in the structure. How that happened was the city and county of San Francisco, in the specification for the concrete for the airport, specified Blue Planet rock be used in the concrete in the airport. And what's important about this is this shows an example how governments all over the world, every country, every city in the whole world, can use their power of procurement to specify carbon sequestered materials as an effective means of carbon mitigation that doesn't cost them anything because they're buying these materials anyway. If we look at rock, which is used around the world, and there's a shortage of rock. In the lower left, you see California, and these are 4 different counties in California. And on the left is the 50-year projected demand for sand and gravel in these localities. And on the right is what's permitted. And there's a fraction, about 30% of what's actually permitted as to what's needed. So when we look at the over 50 billion tons of rock that's mined, it's actually in short supply, even with that much rock mining. If we look at the impact that replacing the mined sand and gravel in concrete today with carbon sequestered sand and gravel, here's some major projects near California. One is our Super Bowl stadium. We could have, in that project, reduced it by 50,000 tons of CO2. A major Salesforce tower in San Francisco, another 8,000 tons. A large dam, over 2 million tons. We're building a high-speed rail system in California. We could save over 6 million tons of CO2 by sequestering it in terms of the carbon footprint. And just to finally show you how this actually would work, this is a projection from the Bay Area Air Quality Management District, which is the regulatory body that regulates emissions in the San Francisco Bay Area in Northern California. And they've set out a course on how they're going to get our emissions down to 1990 levels by the year 2050, and that's the black line here. However, the colored bars represent what's really happening, and this is true all over the world, from the Kyoto Protocol everywhere. We're not meeting the objectives that we've laid out for ourselves. Well, specifically though, if we look in the Bay Area, near San Francisco, where Blue Planet is building a plant right now, there's a potential use of about 11 million tons per year of sequestered carbon dioxide rock. If we replicated that in 5,000 cities around the world, which isn't that many, that would actually translate to over 5 billion tons of CO2 that's mitigated and used profitably in these projects. And just to put it in perspective, governments have funded an enormous amount of carbon capture and sequestration, where you would capture CO2, go through the energetic cost of purifying it, and build pipelines, and then inject it and monitor it and insure it, and treating it as a waste. And our US Department of Energy has spent $4 billion on projects like that and sequestered a total of 16 million tons of CO2. Chevron recently spent $1.7 billion on an offshore injected in the ground project, and will sequester 4 million tons of CO2. And I remind you, there's 1,000 millions in 1 billion. So there's 1,000 million tons in 1 gigaton. So the order of magnitude of impact of what can be done with a built environment is of the right size to actually address the problem. And then to close more specifically, this is the San Francisco Bay Area where we are, and there's a lot of concrete being poured around the Bay Area. There's a lot of construction. We have Facebook and Google and LinkedIn and many other companies, Apple. They're building large projects in the Bay Area and using a lot of concrete. But the actual supply of rock for these projects is very limited, and it's having to be brought in from very long distances. Our plant, it's labeled SFBA on this chart, San Francisco Bay Aggregates, will be producing the CO2 from the exhaust of a power plant in that location. And the red dots show where concrete is formulated and taken to jobs, and they're within 24 miles of the plant. And the green are in about 40 miles of the plant. And that's very important when we're moving massive amounts of carbon dioxide and rock around like this. So the way mitigation of CO2 on this sort of global scale can work practically and be implemented quickly and without costing anything is, let me give an example here in the state of California. Our state, which if it were a country would be one of the leading economies in the world, uses about 240 million tons of rock a year, sand and gravel in all our projects. And it's transported distances of up to 200 miles to get to concrete plants. We spend about $5 billion just on this infrastructure every year. We actually barge in a lot of rock from British Columbia over 1,000 miles away. And like I'd said earlier, only about 1/3 of the quarries are permitted that we need inside the state to supply all the concrete that's being produced and used here. And the distance that the rock is being moved is increasing by over 40% in the last decade because there are fewer and fewer quarries. But to make 240 million tons of rock from carbon dioxide, instead of mining it and transporting it, we would need about 105 million tons of CO2. Remember, limestone's about 44% CO2 by mass. But we could make the state's entire need for rock from CO2. What's important about that is we also have a law, the Global Warming Solutions Act, which has been emulated in other countries around the world, which required us as a state to get to 400 million tons of CO2 by 2020, which we've successfully done. Now we've set the objective to get to about 300 million tons of CO2 by 2030. Well, if we procured all our rock from CO2 sequestered plants in the state, we could meet our goal, our entire goal, without one mitigation measure. And we're doing a lot of other interesting things with electric cars too, but just with one measure with the rock, we could meet our goal. So thank you very much for sharing Blue Planet with your audience. And it's really been a pleasure to be here with you, Peter. So thank you very much.
Thank you, Brent. I don't know if you can hear us applauding you.
Yes, I can.
Okay, all right. Okay, so thank you very much, and please, Peter, join me on stage. We are almost to the end of our event, but we have a few minutes for questions and answers. So if there's anybody here, just raise your hand. There's a question here. Se ti puoi alzare. Okay.
Good evening. I think it's a question for both of you. When we have talked these days and also today about what societies and companies and also politics can do to arouse consciousness about our situation. But what seems to me is that if we don't arouse consciousness between each of us, the situation is, I mean, it's difficult to go to a larger scale. So my question is what we can do as individuals to to lower our carbon footprint or to better the situation, because if we don't do it, to me, if we don't do it in a smaller scale, it's harder to go to a bigger one, so to societies and politics.
So what can we do as individuals? Peter, do you want to answer?
Well, it's a good question, because there was a very famous and cynical science advisor to the British government who said, if everybody does a little, the result will be a little, which is not very helpful to people who want to try and be helpful. But as we've seen from the case of air capture, you do need to have very large-scale support for doing anything really serious about climate change. I mean, we've seen from Brent's talk what a big difference this can make on the scale of a state as big as California. But let's remember, if we want to bring our carbon levels down and get rid of more than 40 gigatons of CO2 per year, that really means doing this on a global scale and with large amounts of support from governments, even though the process itself is actually partly paying for itself through the product. So the best thing that an individual can do probably would be to make use of your democratic rights, to insist that your democratic representatives take this seriously and take this as the most serious thing in the world, rather than something that they don't have to bother with in between elections. So your own behaviour, there are things you can do, like don't drive an SUV, because that's about 40% of people now buy SUVs, and it's the biggest single contribution to the increase in CO2 levels. So that, in other words, we say we're concerned about CO2 levels in the atmosphere, but in fact we're not. We're in fact an incredibly stupid species, in that we, on the one hand, want to do something about climate change, and on the other hand, we go down a showroom and buy an SUV, which is the weight of a tank. So we can do less stupid things than we do, but also we need to push our representatives to take this as the most serious thing in the world.
Brent, do you want to add anything?
I would just add that where the problem is caused by an individual, then an individual can make a difference, such as with an automobile. We can have home solar and battery storage at home, and we can drive an electric car, and that's an individual act. But when it's a large coal-fired power plant emitting 12 million tons of CO2 a year, an individual can't do anything about that except go to their legislators and affect policy.
Ok, thank you. C'è una domanda qui davanti.
Thank you. Good evening. Congratulations. Just a curiosity, does Blue Planet produce carbon dioxide when you produce artificial limestone? It's a question for us, so that I can tell it to the students in my school. Thank you. Thank you so much.
Thank you for the question. Of course, we do pump water and we move rock around, so we have our own carbon footprint. We call that a parasitic load. And it's about 5%, which is quite low. But yes, of course, we do produce some carbon dioxide indirectly through transportation and pumping water and processes like that.
Ok, c'era una domanda qui davanti. Last question, and then we need to close.
Hello. After my colleague said that what can we do individually to try and solve the problem. However, there is a big group of different thinking, I would say, that is led by many leaders of the world, I would say like Donald Trump. So there is a lot of controversy about climate change. However, even if we had to, as you said, democratically put leaders that really help us to change the way we live to solve this problem of climate change, can we really work this out with countries like China, where it is not possible to democratically change it? And if we can do this, can we really, with our walking, really change something in the planet without their help?
Peter.
Well, I guess you could say that there are countries like China that are paying lip service to the need to reduce carbon emissions and are actually doing something, but that it's processes like CO2 removal that can go past that. You've got the big blockage in doing anything about climate change has always been the big countries that stand to actually have to pay out a lot to reduce carbon emissions or to stop using coal, don't want to do it. And so it's a block in human progress set by the selfishness of certain rich countries. But if you can develop a method that will take CO2 out of the atmosphere successfully on a large scale, then you've worked your way around that block. It's just like developing cheap solar and wind-powered systems that even if deep in your heart you'd love to mine more coal, like Donald Trump, if solar and wind energy are much cheaper than coal, then nobody's going to mine the coal, so we save that way. So that it could be that the CO2 removal methods are a way of working around the blocks that are happening.
Brent, do you want to give a final comment on this?
I think what we're learning is that we really don't need to work at the country level. We need to work at the city level. And the C40 mayors have proven this. And it's now international. You know, the mayor of Paris was the head of the C40, and I think the mayor of Los Angeles is the new head of C40. And we see cities mobilizing irrespective of national policies, and that's where we're seeing real traction now.
Okay, thank you. So on this note, do you want to add anything?
I just want to add, if anybody wants to have a look, I've got a couple of small samples of artificial limestone here produced from carbon dioxide by Brent's company. You know, it's a very small sample.
Okay, so on this note, I would like to thank Professor Peter Wadhams and Brent Constantz for joining us tonight in Trieste Next. And have a good night, have a good day in Los Gatos, and thank you once again. Buonanotte a tutti e ci vediamo domani mattina, ore 10, sempre qui al Teatro Miela e nelle altre location di Trieste Next. Grazie a tutti davvero, buona serata.